Hello, my name is Angela, and together with Damian, we will present our work on the topic Learned Models for Cardinality Estimation in Knowledge Graphs. First of all, why is cardinality estimation important? Cardinality estimates, together with other factors such as join ordering and cost models, directly affect the query plan generation. But their purpose goes beyond query optimization. Cardinality estimation is also implicitly a part of approximate query processing, question answering, or even different data exploration tasks. But in order to compute cardinality estimates, it's important to outline the challenges we face when dealing with knowledge graphs. First, present correlation between individual terms make the usage of independent estimates insufficient. For instance, for the following query, although the cardinalities of the predicate title and the object it independently may be quite selective, their co-occurrence can be quite common. Secondly, sparkle queries typically include many joins as depicted in the second star-shaped query. Thus, we cannot assume join uniformity. And finally, queries over knowledge graphs often contain more complex query patterns, for instance, interconnected star and chain patterns. To provide accurate estimates while dealing with these challenges, we developed the LMKG framework. LMKG uses deep learning approaches for detection of interconnection between terms in subgraphs, in the end providing more accurate estimates. Deep learning models also provide the advantage of fast execution while keeping a small memory. LMKG allows the option between two learned estimators, a supervised one and an unsupervised. To overcome the challenges, first LMKG learns over relevant subgraphs and not over independent terms or triples. It provides efficient sampling and compression in the presence of many joins. And finally, LMKG comprises algorithms for handling complex queries. The LMKG framework has two phases. The first phase is called the creation phase, where we decide on which models need to be created. LMKG can create a single model for every query type and size, different models per query type, or different models grouped by the query size. Next, if no sample workload is available, LMKG generates adequate training data, for which in cases of large number of joins, proper sampling is performed. Finally, the chosen models are tuned and trained. The second phase, called the execution phase, includes the user-system interaction. Once given, the query is decomposed if needed, forwarded for encoding, and finally used for prediction of the final estimate. Now, as we mentioned, there are two versions of LMKG models. The first model that can be created is a supervised estimator termed LMKG-S. For a given query, the model learns to predict its estimated cardinality. The training data contains queries and their true cardinalities, where the queries include at least one unbound term. If a sample workload is not available, LMKG-S creates sample queries from the given knowledge graph. The model minimizes the Q error, which is the relation between the true cardinality and the estimate. As depicted on the figure, for all considered datasets, we can notice that the cardinalities of the queries follow a skew distribution for which a proper scaling is needed. The intuition behind the architecture of LMKG-S is combining typical subgraph representations and the capability of simple deep learning models for efficient cardinality estimation. Given a query, the encoding produces three separate parts: tensor A, representing the interconnections between nodes with the adequate predicates, matrix X, representing the nodes, and matrix E, representing the predicates in the subgraph. The separately encoded inputs are optionally independently forwarded to initial layers, then concatenated and forwarded to final feed-forward layers for estimating the final cardinality. To represent the subgraphs, we propose a new subgraph encoding termed RG encoding. As an example, consider the shown star query. In step 1, a global mapping of the terms to an integer ID is created. Once the query is given, an ordering of terms is created for the given query, where the global IDs of the terms in the knowledge graph determines their order in the query as shown in step 2. Finally, for a predefined maximal size of the queries, the encoding is created, resulting in tensor A and matrices X and E. Therefore, for the sub-pattern book has author Stephen King, if we look at tensor A, has author is the first predicate in the edge order, the variable is the first node, and the Stephen King is the second node in the respective node order. The bits in X and E indicate the types of the nodes and the edges.
LMKG-U is our unsupervised cardinality estimator, which represents a deep autoregressive model, chosen because it can efficiently learn the correlation between the present terms. We train LMKG-U on subgraph patterns with bound terms, where the encoding is a concatenation of all the terms in the given query. The output will contain the densities for each term, conditioned on the values of all preceding terms. So by multiplying the conditionals, we can obtain the probability for the query, and then the cardinality can be estimated by multiplying this probability with the size of the training dataset. The model is trained on subgraph patterns of specific size and type. However, for heterogeneous knowledge graphs, the creation of all such patterns creates an intractable problem. So we employ random walk sampling to create samples with similar properties as the knowledge graph. To be able to answer queries involving variables, we employ wildcard skipping. To do this, during training, a randomly chosen subset of terms has their values masked, which actually means replaced with a special token that denotes a variable. In LMKG-U, we use the pattern-bound encoding tailored to a certain type of query. For instance, given the example star query, the encoding requires ordering of the predicate-object pairs connected to the subject. So, first, a mapping of the nodes and predicates to an integer ID is created. Then, a serialization of the specific query type pattern is performed and encoded using one-hot or binary encoding. In chain queries, the ordering of the nodes and predicates is intuitive, after which the same procedure is performed. However, for heterogeneous knowledge graphs, the number of terms can result in enormous encodings that can cause extremely large models that are hard to execute. Thus, we propose a lossless compression, which splits a term into several subterms, having together a much smaller number of unique values than the original term. So far, we have shown how our model works for specific query types. But there can also be complex queries, such as the one shown here, which consist of more than one query type. So for LMKG-S, the handling of complex queries is directly possible by the SG encoding. But for LMKG-U, since it trains on specific query types, to capture complex queries, it would require the creation of an unrealistic number of models. Thus, we leverage the capability of LMKG-U to create samples conditioned on previously specified terms. So first, the complex query is decomposed into star and chain queries for which models exist, and the subqueries are ordered based on the join relations. The first subquery is sent to the appropriate existing model, and the model produces a cardinality estimate and also generates samples for the terms that need to be joined with the following subquery. The join variables of the second subquery are then fixed to the generated samples, and this same iteration is repeated for the remaining subqueries. In this way, several different paths and path probabilities are created, and the final estimate for the complex query will be an average over these independent paths. We performed experiments on one synthetic and two real-world datasets, and as competitors, we chose a wide spectrum of approaches that can be grouped into three groups: summary-based, sampling-based, and learning-based approaches. First, we investigated the accuracy of the approaches when varying the query size. So the x-axis represents the considered query size, and the y-axis the average QR, which is log-scaled. On the left side, we have the results for SWDF, and on the right side, the results for LUBM. It is noticeable that when considering the different query sizes, the approaches to LMKG outperform the competitors. Unlike the other approaches, LMKG-S is not impacted by the number of joins, and LMKG-U shows a more constant performance. The competitors are mainly affected by the number of joins, where even some approaches could not be executed for all of the join sizes. Next, we evaluated the accuracy when varying the query result size. So the x-axis depicts the considered query result sizes, which are grouped into buckets with boundaries defined by log with base 5. From the results, we can directly observe the problems of the LMKG-S approach. LMKG-S is highly prone to outliers, which is visible for the higher ranges. So this actually means that LMKG-S is mainly impacted by the skewness. On the other hand, LMKG-U produces more constant results throughout the ranges. We compared the memory consumption of LMKG with the two summary approaches and MSCN and NeuroCard. LMKG-S requires less memory than LMKG-U, and the memory of LMKG-U increases with the number of involved terms. Compared to NeuroCard, LMKG-U also requires more memory. But this is not a result of a better term compression, but of the different encodings used. So NeuroCard uses embedding on top of the input, whereas LMKG-U uses only binary encoding. We evaluated the execution time of the approaches for the different query sizes, and the y-axis shows the scaled average execution time in milliseconds. LMKG-S outperforms all the approaches except the characteristic sets approach for the LUBM dataset. It is also interesting to note that LMKG-U outperforms Wonderjoin and NeuroCard, and this is because LMKG-U requires only a single forward pass for estimating the cardinality. Finally, we evaluated the accuracy for complex queries and varying the query result size. And from the results, it is clear that LMKG-S outperforms all the competitors for every query result size. When analyzing the results for LMKG-U, it is also noticeable that if we relied only on the independence assumption, the produced estimates would have been much worse. This underpins the importance of the proposed estimation approach for LMKG-U. To summarize, we addressed the problem of cardinality estimation in knowledge graphs by using both supervised and unsupervised models. We showed that LMKG outperforms the competitors in terms of accuracy while keeping a small memory footprint and requiring less time for producing estimates. And our models answer the challenges by capturing the correlations between individual predicates, capturing many self-joins, and being able to answer complex queries. With that, we would like to thank you for your attention, and for more details, please check out our paper.